Hi everyone, welcome to this course again. So we have been discussing LLM efficiency. So last lecture we discussed model pruning, where we discussed different types of pruning techniques. Generally there are three ways for model compression. One is model pruning, other is model distillation, another is model quantization, right? So in this course we will only cover, we are planning to cover model pruning and model distillation. We will not cover model quantization. In the last year's lecture, we briefly talked about quantization, but this year we will not cover quantization. So in today's class, we will discuss distillation. We will see different types of distillation methods and the pros and cons of different methods, and we will try to interpret or try to explain distillation methods very briefly. But before that, this is today's breaking news. On September 12th, Qwen 3 Next 8TB A3B model was released. This is Qwen's first model on the next generation foundational models, and they are saying that this is optimized for extreme context length and large scale parameter efficiency. So in the model they came up with these two modifications. The first one is gated delta net and the second one is gated attention, right? Gated delta net, some of you know, it basically looks at the delta difference between two representation outputs. So if you look at two consecutive layers and their outputs, right, you can measure the delta, right, the difference between two representations, and the model tries to learn the difference, not the representation, the actual representation. Now why this is important? Because you can quickly learn the delta in comparison with the entire representation, and they said that if you use delta net, that can improve the speed quite significantly. And the other one is gated attention. Some of you know, in gated attention, so what we do is that we similar to LSTM kind of mechanisms, right, we here also we incorporate gated mechanism during the attention computation, right? So what you do is, let's say when you so attention is nothing but the weighted sum of values, right? So after, I mean, once you get the weighted sum of values, you put an attention on top, or you put a gate on top of that, right? And that would control the attention mechanism. So it is not that maybe for a specific token, some tokens are not that important, although attention inherently captures that, but using gate you can even better control that mechanism, right? Maybe some tokens are not at all useful for the given token and so on and so forth. So they said if you use gated attention, that would improve the performance. So you can look at it. Qwen as usual is a open source model. You can use it for your project. Okay. So model pruning we discussed last class. Model distillation, okay, in today's class. What is model distillation? So the idea is that you have a large you have a larger teacher model and a smaller student model, right? Let's say you have a 175 billion model, which is called teacher model, right? And you have a small model, let's say 7 billion model, we call it student model, right? And this student teacher paradigm is a unique paradigm in knowledge distillation. So it is called teacher student paradigm. By default, we know that this teacher model, since it's a big model, it knows many things better than a student model. In a classroom setup, you can think of teacher, right? Assumption is that teacher knows better than a student, right? Sometimes this assumption may not hold, but in general that's the assumption. And again, in a normal classroom setup, a teacher teaches students, so basically a knowledge flows from the teacher to the student, right? Here also we have some mechanism called the knowledge distillation. Through that we will distill or kind of transfer knowledge from a teacher to a student. It sounds like a sci-fi movie, but it's not a sci-fi, nothing sci-fi as such. This is actually very simple. But last 3, 4, 5 years, people have been developing on this, and some of you know, whenever people release these days, whenever big companies release these models, big models, right, Cohen, Llama, GPT, they also release a quantized distilled version of their large model, right? So we'll discuss different distillation methods in today's class. Okay, so distillation, knowledge distillation, idea behind knowledge distillation was proposed by J. Filton in 2015, the first paper on distillation, and the idea was very straightforward. The idea was that that time there was no transformer, there was no LLM as such. So they used, J. Filton used a simple CNN, right? Let's say the task is to classify an image, input is an image, and you have a teacher model which is a deep neural network, deep CNN, for example, and let's say it's a simple binary classification problem, dog or not, right? And so the model produces some distribution over dog and not dog, right? So you have a logic distribution of dog and not dog, right? Similarly, you have another model which is a student model, a small model, right? Let's say a shallow neural network, right? And again, if you give the same input to the student model, it also produces a distribution over dog or not dog, right? Now here the logic distribution and the logic distribution here, they are different, right? And the distillation, what is the target of the distillation? The target is to basically minimize the difference between two distributions, right? So the idea is that the more you minimize the difference between two distributions, the closer the student model basically be towards the teacher model. So what's the loss? So the loss is as follows. So you see, y hat t is the logit of the teacher model, and y hat s is the logit of the student model, right? And you pass it through softmax, and that will give you a distribution. It's a distribution, this is also a distribution, and you minimize the let's say L2 norm, right, between the two. Simple idea, right? But the only point here is, once you calculate the loss, so this is your loss, the loss gets propagated only through the student model. The teacher model remains frozen. Okay, so only the student model gets updated, and over the iterations this loss difference gets reduced, and the student model comes closer to the teacher model. Simple idea. Then later on, in 2019, right, this TinyBot paper came. Some of you remember the paper TinyBot, right? And there they said that KD loss, so this is called KD loss, remember this term, KD loss, knowledge distillation loss, right? So they said that KD loss is fine, but we should also look at layer wise loss. Okay, let's say it's so this is your teacher model, this is your student model, right? And teacher model has 12 layers, student model has 6 layers, right? Let's say bot large and bot small, right? And you look at the representation coming from, let's say, layer I here and layer I here, right? And this is the representation of layer I of the teacher model. This is a representation of layer I of the student model, and then you minimize the difference, right? Now here the question is, number of layers is different, right, for the teacher model and the student model. For teacher models there are 12 layers, student model there are 6 layers. So how do you make a correspondence between ith teacher layer and ith student layer? So what they said is that you don't need to look at all the layers, you only look at top 4 layers, for example, or top 5 layers, right, or top 3 layers, and then you compute this loss. Again, so they suggested that along with the KD loss, you compute this layer wise loss, and you take the sum of them, and then you backpropagate this loss only through the student model. So, and over the time, people have proposed different other loss functions. For example, since these are two different distributions, teacher distribution and the student distribution, you can use Kale divergence loss, for example, right? So normal Kale divergence loss can be used. People also said that normal Kale scale divergence laws has certain limitations. They proposed reverse scale divergence laws. So normal scale divergence laws or the forward scale divergence, where let's say there are two distributions P and Q, right? So this is PT log P by PT by QT, right? Now let's say PT is a distribution of the teacher model, QT is a distribution of the student model. Then you take the scale divergence between teacher and student. The reverse case scale divergence is just the reverse one, right? So QT log QT by PT. You can also use Jensen-Shannon divergence and so on and so forth. For layer wise distance calculation, you can use L2 norm, L1 norm, cross entropy, and so on and so forth. And all these types of loss functions were used in different methods. But if you look at broadly KD in general, right? Broadly, you can classify KD methods into three buckets. Okay. The first bucket is called white box KD method. What is white box KD method? In white box KD, you assume that the teacher model is white box, meaning you know the layers, you know the intermediate representations, you know the logic, you know everything, right? And accordingly, you calculate the loss and backpropagate the loss through student model. Black box KD, you assume that you do not know anything about the teacher model's configuration. You only know the output. Right now, from the output, how do you then distill? And this is very difficult. So, black box KD is not a very popular approach. In between white box and black box, there is another method called meta KD, meta knowledge distillation. What is the idea here? The idea here is teacher will so the student model distills knowledge from the teacher model, but there might be an intermediate teacher model or a meta teacher model, right, which will guide the entire distillation process. Right now, think of again a classroom setup. Let's say there is a teacher, there are students, and there is, let's say, a class monitor or class representative. Right, the task of this class representative is to first assess the overall knowledge of the students, and the representative will talk to the teacher saying that, look, out of 50 students, 30 students know about linear algebra, remaining 20 students don't know about linear algebra, and so on and so forth. So you teach students accordingly. Okay, so the concept of meta teacher, and meta teacher guides the teacher model how to distill knowledge from teacher to student. So we will discuss white box and meta KD here. Okay, so the first paper after Hilton's paper in 2015, the next paper came in 2016, and here the idea is simple. The idea is that, now remember, I forgot one point. When you measure the logic difference here, right? How do you? So you measure the logic difference with respect to the ground truth. What do you mean by this? Let's say the task is sequence generation problem, right? Let's say your ground truth says that the next sequence is going to be I am hungry, right? So ideally you should generate this sequence, right? This is the ground truth, but it may happen that the teacher model also doesn't generate this specific sequence. Student model also doesn't generate this specific sequence, right? So once you find the logic distribution from the teacher model, you look at the logic for I, you look at the logic for am, you look at the logic for hungry from the teacher. Similarly, you look at the logic from student for these three tokens, and then you measure this difference. Okay, so this is the default distillation process. The default distillation process says that you have a ground truth, you look at the corresponding logic from the teacher, you retrieve the corresponding logic from the student, and you minimize the difference between these two logics. So in 2016 paper, they said that the ground truth based KD may not be ideal we should look at the teacher's output, right? Because after all, the task is the target is to move the student closer to the teacher. So whatever the teacher articulates, the student should also articulate that. Forget about what is the ground truth. This is the idea here, right? So here what we will do, here we will not measure, or here will not retrieve the logics corresponding to ground truth. We will retrieve logics corresponding to the output generated by the teacher model. But what is the problem here? That is okay, but what's the problem here? The problem here is that for that you actually need to do some sort of decoding, let's say beam search, for example. Otherwise, how do you generate the sequence? From the teacher model, you need to, so once all the layers are processed, right, at the end you need to do some sort of beam search, otherwise how do you generate the sequence, right? And beam search is extremely time consuming. But that's fine. They said that you do not rely on ground truth, because during the test time you will not have any ground truth as such. So better you retrieve the logics of the sequences generated by the teacher model, and then you minimize the logics of teacher model and the student model. Okay, so as I mentioned, beam search is computationally expensive, right? And the other problem is that it may happen that the teacher generates a wrong sequence, right? So ideally, in a normal classroom setup, right, I mean, whatever a teacher articulates should be correct, right? And it should also follow some textbook, for example, right? Let's assume that the textbook is a ground truth for us. But it may happen that in sometimes a teacher articulates something else, something wrong, and that should not be propagated to the students, right? So the error may also propagate. Okay. So in 2023, now let's look at some of the loss functions. So as I mentioned, the default loss function is the KD, the KL divergence loss between the teacher and the student, and this is called forward KL divergence, right? So look at here, let's say this is a prompt X, right? I mean some input, right? And you get the logic from student, which is Q theta, and you get the logic from teacher, which is P, and then you measure the KL divergence between P and Q, right? So the problem in this paper, so in the MiniLLM paper, that what they showed is that if you use forward KL divergence, the problem is that the student models starts overestimating the low probability region. What does it mean? Let's say your ground truth distribution looks like this. This is your ground truth distribution. Okay. Now, if you use forward KL divergence, you see that the model will start learning a distribution like this. Now these are the low probability region, but the model overestimates this low probability region, right? So they analytically and empirically showed that if you use reverse KL divergence, which is KL divergence between Q and P, that would solve this problem, right? So you may end up basically learning a sample, learning a distribution like this. Like this. Okay. Now, in the follow-up paper 2024, this GKD paper, in GKD paper they said that in case of this paper, right? In this model, they argued that we should not use ground truth. We should use the sequence generated by the teacher model. But in the GKD paper, they said we should not use the sequence generated by the teacher model. We should use the sequence generated by the student model, right? And what is the logic behind this? The logic is that, the logic is as follows. So what they are saying is that during the test time, we will not have any teacher model. We'll have only the student model. So the task is that whatever the student model articulates, we should try to rectify that articulation. it is not that the teacher model, the student model will start mimicking the teacher model. It is so the ideal case, it should be whatever the student model articulates, the KD method should refine that articulation, right? So it means that let's say the student model generates, let's say the ground truth is I am hungry, right? And the teacher and the student model generates I am rich. Okay. Ideally, if the teacher model is good, the probability corresponding to rich should be low, right? And the probability corresponding to I am and should be high, right? But for the student model, this is high, this is also high, this is also high. Therefore, the model generated the sequence, right? Again, we need a beam search. So beam search problem is still there. So then they said that you minimize these two distributions. Okay. Now in the figure you see here, that they said that if you use GKD, right? So this is the performance of GKD, and GKD with different variations, with one policy, with mixed policy, with supervised KD, and so on. GKD always outperforms other. The follow-up paper 2024, as you see, all the papers are recent papers, right? Now, what is SGO? SGO is called self-generated output. Self-generated output is the output generated by the student model. So, in the DistiLLM, the recent paper, adaptive SGO, self-generated output, in this paper they said that, as you rightly mentioned, that we need both the ground truth and the teachers and the students' response, right? From the ground truth, the student gradually learns what to articulate, right? From the students' response, and if we minimize students' response and the teacher's response, the student model will learn how to mimic a teacher model. So both these things are needed. Okay. So what they said is that, let's say, I have a fixed data set D, and this data set is the ground truth data for me, okay? And we will use another data set, or we will curate over the iteration, we will curate another data set, and we call the data set replay buffer. So DR, so we have DR and we have D, right? Initially DR is empty, right? What is going to be added to DR? The students' responses will be added to DR, okay, over the time. So initially the distillation happens with respect to ground truth, and over the time you will not use ground truth, you will start using the students' response for distillation, right? So as you see here, this is random variable U, right? You sample the value of random variable between 0 to 1 from a range from a uniform distribution ranging between 0 to 1. If the value of the random variable is below a threshold, so phi is a threshold. If your value is below the threshold, you look at this DR, right? And you sample instances from DR, and you retrieve the logic from the teacher, you retrieve the logic from the student, and you calculate the KL divergence, right? But if U is greater than equals to phi, then you essentially retrieve the ground truth data, right? And you do the same thing, right? And over the time, this threshold value phi, right? The threshold value gets reduced, meaning that over the iterations you start retrieving only the students' responses, not the ground truth. In 2025, a recent paper, they showed that both the forward KL divergence and the backward KL divergence both are important, right? And look at this visualization. These visualizations are very interesting. So they showed that now this gray distribution, this is my ground truth distribution, okay? Now if you use forward KL divergence, as I mentioned, it basically it will produce a smoothened distribution, right? Which will overestimate the low confidence region, right? Whereas if you use reverse scale divergence or the backward scale divergence, it would produce this kind of distribution, which will rightly identify the peak, right? But at the same time, this kind of distribution fails to identify low probability zones, right? Meaning it underestimates the low probability zones, right? So what they said is that if you do some sort of alpha weightage of the reverse scale divergence, you will start seeing a distribution which is kind of mix of this, right? But ideally what should be needed is that some sort of alpha beta combination of scale divergence and reverse scale divergence, right? They said that you do alpha beta weightage, so alpha times forward scale divergence plus beta times backward or the reverse scale divergence, where alpha beta is not a convex sum. It's not like alpha 1 minus alpha, right? So if you do that, you will be able to get this kind of distribution, right? Which would less overestimate the low probability zone and less underestimate the high probability zone. Okay. All right. So till 2025, all these models were proposed. But if you look at all these models, the basic problem here is that the distillation process is always unidirectional. What does it mean? Meaning that the teacher model does not know anything about the student's capacity. There is a KD loss. You can use scale divergence or reverse scale divergence, and there is this layer-wise loss, right? You minimize this loss and you backpropagate the loss to the student model. The teacher model doesn't know anything about the student model. The teacher model remains frozen. So the basic limitation is that the knowledge sharing is unidirectional. Teacher is not aware of student's capacity. To address this, in 2022, right, another paradigm of distillation started emerging called MPDistil. So the idea behind MPDistil is that we will teach the teacher model how to teach. Okay, it's called teaching a teacher. So here the idea is simple. The idea is that, let's say you have this paper. In this paper, what they said is that, let's say you have a teacher model T and a student model S, and let's assume that it's a white box teacher model, right? So what you do first, you first replicate the student model. You have S dash. S dash is just a replica of S, because I don't want to touch S for the time being. Therefore I create a replica of S, which is S dash. Okay. First, what you do a simple KD, right? A simple KD means you have a KD loss here, right? A KD loss plus layered loss, layer wise loss if you want. You measure this KD and layer wise KD, right? And this loss gets propagated only through this replicated student model. A simple approach, simple KD approach, right? So far, teacher doesn't know anything about the student. Only student model gets updated. Only the replica of the student model gets updated. The actual student model is still untouched. Okay. In the second step, what you do? In the second step, now look at here. In the second step, I use another data and I call this data quiz data. A quiz data, right? And what is the purpose of the quiz data? The purpose of the quiz data is that I'll give this quiz question to the teacher, to the student, right? I will see how students perform, and I will check their scripts, their answers, and from the answers, I will try to rectify myself or update myself, right? So far, the teacher has not seen the answer of the student. Now, what I'm saying is that I will introduce a new data called the quiz data. I'll give the quiz to the students. The students write the answer. You measure the loss or the error, and that error gets back propagated end to end through student till teacher. Okay. Now this loss This cross entropy loss is the loss on the quiz data based on the performance of the student model, right? This loss gets back propagated end to end to teacher. In fact, this is a bit tricky step. The reason is that so in this stage, what I do, I basically calculate two losses. One is the loss based on the quiz data, other is the loss based on the training data, a normal training data. So I have a KD loss, I have a cross entropy loss. The KD loss only gets back propagated to student, right? But the cross entropy loss gets back propagated to student till teacher, right? So at this stage, the teacher knows what the student, where the students made mistakes, right? And that their parameters get updated accordingly. Now the third step. So the third step, what you do, you repeat the same KD process again. A same KD, a normal regular KD. And here, when you measure the KD, remember the teacher model already gets updated, already got updated previously, right? So the logic that the teacher model produces here would be very different from the logic that it produced at the beginning, right? Now here again you do KD and that gets back propagated to student. But here remember this is actual S, actual student model. Till this part we had a replica of S, right? But now we have an actual student model. So the actual student model gets fine-tuned with respect to the updated teacher model. That's the difference. Is clear? So this is called this is called student aware distillation. Now this was proposed in 2022. In our lab last year, we showed that this is not enough. Student aware distillation is not enough because a student aware distillation only gives you the flexibility that the teacher gets refined based on the output of the student. But there are some other aspects also. What are the other aspects? The other aspect is, in a usual classroom setup, so far all the KD methods that I mentioned, there is always a collaboration between a teacher and a student, right? Because the teacher tries to rectify themselves based on the feedback, right? The student also tries to rectify themselves based on the teacher's feedback. There is always a collaboration. There is no competition as such. But if you think of a normal classroom setup, there are few students who ask a lot of questions to the teacher, and sometimes the teacher also is not able to respond to the questions in the class, right? And the questions are tricky. So what we said is that in the distillation process, let us incorporate the notion of healthy competition between a teacher and a student along with the collaboration. Okay, I said healthy because it is not the case that the student will always try to beat a teacher, or a teacher will always try to beat a student, right? But it's a healthy competition, meaning that the two factors, collaboration and the competition, is balanced in some ways. And we call this method MPDistil, right? Student aware meta distillation process. And this method has 4 steps. First 2 steps are simple and the usual steps, and let's look at the step. The first step is teacher fine tuning. What is teacher fine tuning? Again, we assume that the teacher model is a white box model. Okay, so we have the data set, we have the ground truth data, right? We calculate the loss of the teacher model with respect to the ground truth, and that loss gets propagated only through the teacher. Now I have not mentioned this step in the previous models, but this step is always important. If you have the flexibility to fine tune your teacher model also for the specific task, right, you should do that. Okay, now it can be a LoRa fine tuning, a simple LoRa fine tuning, or only one layer fine tuning. Whatever data sets you have, you should fine tune your teacher model with respect to the task specific data set first. Okay, so this is teacher fine tuning. So now after this stage, the teacher knows about the task. Step 2 is student distillation. Again, this is the usual process. I have the teacher, I have the student, I have the task specific training data, right? And the loss function that I calculate here is what? This is a simple student's loss. Now look at this logic. This is ACE, right? This is student loss with respect to the data set, right? And what is this? This is KD, right? Simple KD loss. And what is this? This is layer wise loss between layers. So this is task specific loss of the student, this is KD loss between teacher and student, and this is layer wise loss between teacher and student, and we have some alpha 1 minus alpha beta weightage, right? And remember, this loss only this loss will be backpropagated only through student. Step 3 is most important. So in step 3 we introduce a concept of meta teacher. What is a meta teacher? A meta teacher is a simple multilayer perceptron. You see a simple multilayer perceptron. And what is the task of the meta teacher? The task of the meta teacher, the meta teacher is a stricter version of a teacher. Meaning it will always prefer the teacher model. Right? A teacher can be lenient, but a meta teacher is always strict. Right? And let's look at this meta teacher and the input. So the input to this meta teacher is, there are two inputs. The first input is the representation of the student model. So you have teacher model, student model. You retrieve the last layer representation from the teacher, last layer representation of the student, and these two representations will be given to the meta teacher, right? And what would the meta teacher do? Don't worry about this equation, right? Just follow what I'm saying. So the meta teacher will calculate this loss. Look at the first loss. The first loss is called the collaborative loss. If you look at this equation here, right? What is this equation? What is this component? This is the log logit of teacher. What is this? This is the log logit of student. Basically the logit of teacher and logit of student. You take the sum of teacher and student's logit, right? And you want to maximize this. Now you see this minus, because I want to minimize the minus of that, which means I maximize the teacher's loss, the teacher's logit, and the student's logit. What does it mean? What does it mean? What is the meaning of this loss? If I maximize both the logits, what does it mean? I prefer both teacher and student, and this is called collaborative loss. You collaborate, right? At the same time, there is another loss called the competitive loss. And what is this competitive loss? You only look at this part. So this is teacher's logit, and this is student's logit, and you take the difference between teacher and student's logit, and you want to maximize this. What does it mean? Either you maximize the teacher's logit or you minimize the student's logit, then only the difference gets maximized. It means you give more preference to the teacher. Okay, so you have a competitive loss and you have a collaborative loss. Now either you can add them and do some alpha beta weightage, or you can play with them separately based on your task. So after the third stage, you obtain a meta teacher, which is a simple perceptron, right, which will give preference to the teacher model. Fourth stage. So now what you have a meta teacher and a student. I don't need a teacher anymore, because I use teacher to train this meta teacher. So this is my meta teacher and this is my student. I have a quiz data, right? Based on the quiz data, I look at the performance of the student model with respect to the meta teacher's output. Otherwise, you can't calculate the loss, right? So this is my loss with respect to the quiz data, right? And what I will do now, I will refine my student model. So far, I have not refined my student model. Have I refined? No, right? I only refined my teacher model at the beginning. But I refined the student model here. But here in second stage, I only considered 3 facts, 3 losses. The first one was KD loss, the first one was task specific loss, second one was KD loss, and the third one was layer specific loss. Based on that, I refined student model there. At step 4, I will refine the student model again. But how do you do that this time? So here I incorporate a policy learner. The policy learner we all know, right? We have seen policy learning in alignment, right? So I incorporate a policy learner. It's again a simple perceptron. And what is this policy learner doing here? This policy learner is also called a curriculum learner. How many of you know curriculum learning in machine learning? Have you heard of curriculum learning? You haven't heard of curriculum learning before? So in curriculum learning, what we do is that we give simple instances, right? Simple instances meaning those instances which can be easily classified, right, to the model, and then gradually increase the complexity of the instances, right? So you first start training the model with simple instances, and then you increase the complexity of the instances. It is like, let's say you want to learn LLM, right? You are given a curriculum. You first learn linear algebra, and then machine learning, and then NLP, and then LLM. There's a curriculum, right? So you first learn easy tasks, easy courses, and then you learn difficult course. Same idea here. So so here this policy model, this policy learner, what it does, so let's say I'm interested in the task sentiment analysis. This is the task for which I want to distill my student model, the task that I've been given. I also know other n number of tasks. Now what are these tasks? These tasks are ready-made tasks available in the literature. Let's say emotion detection, machine translation, NLI, right? These are the existing tasks which are already out there, for which the data is already given. So the policy learner will choose tasks from the task bench one by one, right? And the student model is trained based on the task. So you have n number of tasks here. The policy learner will choose one task from the task bench. That task data set will be given to the student model. Student model gets refined, right? And again perform the quiz task, the actual quiz, right? Then you measure the error, right? The error will basically be used as a reward, right, for this policy learner. And then now the circle is complete, right? So let me again summarize the last stage. You have a meta teacher, you have a student model, right? You see the performance of the student model with respect to the quiz data, right? You get some sort of error of the student model. That error will act as a reward for the policy learner. So this will be fed to the policy learner. The policy learner will try to understand which task to be chosen for the student model. The policy learner will choose that task. That task will be given to the student model. The student model gets refined. Again, the student model appears for the quiz. Calculate that. Again, you measure the error. Error will be given to the curriculum learner, the policy learner. Policy learner gets updated. Again, based on that, policy learner will choose another task. That task will be given to the student model, and the model gets refined. And this process will go on and on until unless, let's say, you have some convergence criteria. Let's say after n number of iterations, or let's say you stop when the error with respect to the quiz data comes below a threshold, and so on and so forth. So this is the idea. So we incorporated two factors. One is this meta teacher and the other is this curriculum learner. Yes.
Why is the meta teacher needed in the course?
So the very good idea. So very good question. Why is the meta teacher needed here? Because, can you tell me? Can somebody tell me why the meta teacher is needed here? What do you think? What do you think? If you do not use meta teacher, how do you incorporate the notion of collaboration and competition at the same time? So meta teacher is trained on these two different loss functions. How do you incorporate the notion of competition in the model? I need some intermediary model which will take care of this factor.
And second thing is that meta teacher also, it was an MLP, right? So it requires output from teacher and student to go.
Yes, here. Step 3.
So then ideally the meta teacher output also has a pass to the student and teacher. Is it?
No. Meta teachers.
So when we are saying that we are producing output to meta teacher in the fourth step, what do we?
In the fourth step, what you do, so given this quiz data, so you have a quiz data, right? The quiz data is given to the teacher, right? The teacher's output will be passed to the meta teacher. The meta teacher will produce a representation, right? And the student also produce a representation, and you measure the difference.
Also, sir, in this, like, when we are doing distillation, first we are fine-tuning on a task, right? But then we are using the policy learner to diversify across tasks and train the student.
Yes.
So doesn't that somehow lead to forgetting of the initial?
No, that's the very good point. In fact, we observed that if you do this kind of curriculum learning, this would help you improve cases where your test sample comes from out of distribution samples, out of distribution region, right? And it would always diversify a student's capacity, a student's capability. We also showed that if you use this kind of curriculum learning, you need very small amount of data, task specific data for fine tuning the student model at the beginning. Now, so all these things are good, but the most impressive output or the most impressive result is as follows. So I'm showing, don't worry about the table, right? So the impressive output here is, so we tested our method on glue benchmark, super glue benchmark, big bench, and so on across whole 24-30 tasks. There are some tasks where a student model actually beats a teacher model. Now think about it. So the goal of a student model is not to beat a teacher model, right? What is the goal? The goal is to come closer to the teacher model. But we have seen that due to all these modifications here and there, now these numbers indicate, now if the number is negative, that means so the number indicates that the result, the performance difference between the teacher and the student, between the student and the teacher, right? Student's output minus student's performance minus teacher's performance. So if the numbers are negative, that means teacher is better, right? But if you look at here, the number is 0, the number is positive, positive. It means that the student model is better than a teacher model, which is extremely counterintuitive, right? Currently we are trying to understand why this is happening, right? When I presented this work in different forums, people said that this may happen because of overfitting, but there is no chance of overfitting. We cross-checked. In fact, we are diversifying the model, right, with different tasks, so there is no chance of overfitting, and so we also do not know why this happens. We are currently working on that. Okay, so we have looked at white box distillation, meta distillation. Now let's try to understand what distillation implies, right? and this is again this year's ACL paper, our ACL paper. So we showed that it is well known that the distillation process always improves the generalization ability of the model, but what we are trying to understand is whether after distillation the student actually mimics the teacher or what, right? And what are the key drivers which influences the distillation process altogether. So to do that, we took different pairs of teacher student models, right? Let's say, and here I'm showing the result for the Queen model. So let's say we have a teacher model of 14 billion Queen model, and we have different student models, 0.5 billion, 1.5 billion, 3 billion, 7 billion, and so on and so forth. And what is the agreement? Agreement is the overlap between the final output of the two models, right? Let's say a math reasoning task, if both the outputs of the teacher and student agrees, right? If they agree, if they are same, then they agree, otherwise not. Let's say a simple math reasoning task. Let's say GSM 8K, math arithmetic, right? Add sum, all of them are math related tasks, right? So if both of them produce the same result, then they agree, otherwise not, right? So we observed that if you look at the difference, so the blue line is before KD and the red line is after KD. You know, if you look at the gap between blue and red here and blue and red here, right? This is more prominent, right? What does it mean? It means that if the size difference between the teacher and student is larger, then you see more gain compared to this, which is intuitive. It is saying that if your student model is really small, the KD always benefits. Okay, let's now look at two other simple metrics. The first one is called the fidelity. The fidelity between teacher and student. What does it mean? Let's say you give a reasoning task to a teacher model and a student model. The teacher model produces a reasoning trace, and student model also produces a reasoning trace, right? You not only look at the last output, right, but also looks at the step. You look at the step, right, the steps that they produce, and also the output. So the output you have already checked before in the agreement plot, right? Now you look at the steps, right? So it may happen, very interestingly, it may happen that the agreement is very high, meaning the final output is the same, but the steps are different, right? It may also happen, the other way around can also happen, meaning the steps are the same, but the final outputs are different. Meaning at this last stage, maybe the model makes some mistakes. For example, if you look at here, the steps, I mean, how do you measure the steps? I mean, we did a simple approach. We just looked at the representation, the embedding of the trace, reasoning traces, and measure the similarity, right? So here you see, if you look at these steps, steps are the same, but the outputs are different, right? So high agreement, but a low fidelity. Here, same. So here you see that. So here I think low fidelity. Here high fidelity, right? But the wrong answer. The answer is wrong, and here the same answers are produced, right? But the reasoning steps are different. This is just a sample example. So now let's look at some of the drivers. I mentioned earlier at the beginning that if you have capacity to fine tune your teacher model, that will always be useful, right? If you have data set to fine tune your teacher model, even one layer or a lower fine tuning, that would be beneficial, right? So here we showed that, let's say you have two types of teacher models. One teacher model is a generic ChatGPT kind of model. Other teacher model is, let's say, a 175 billion open source model, which is fine tuned on the task, right? You should always choose this one, not this one. So generic highly capable model is not good enough compared to a task specific teacher model, right? You see this blue bars indicate KD with teacher aware or task aware teacher, and orange bars indicate KD without task aware teacher, and with task aware teacher is always better than without. Then what we did, we started injecting noise to the logic, right? We have the logic distribution, right? Now you start injecting noise, and we see we try to understand how much or till how long the model can tolerate this noise, right? So we sample noise from a distribution, from a Gaussian distribution, and you observe that it can tolerate noise up to certain level, but suddenly we see a drop, right? The third one is, I hope you remember the temperature parameter, right? We used it in the softmax, right? E to the power z by t, right, or tau. And let's look at this importance of this temperature parameter in KD, right? Some of you know that if you increase the temperature, what would happen in the distribution? Huh? What does it mean? I mean, in terms of smoothness, what would happen? Uniform, right? If you increase the temperature, the curve tends to become kind of uniform, right? Whereas if you decrease the temperature, it will show some sort of spike. So we observed that if you increase the temperature parameter, right, the recall of the student model will increase. Is it intuitive? If you increase the temperature parameter, the curve gets smoothened, uniform. What does it mean? It will increase the recall or precision? Tell me. It will always increase recall, right? If you decrease the temperature, it will start peaking, it will start identifying the spikes, right? Meaning that high probable outputs will be returned, right? And whatever you return will be correct, meaning the precision will increase. And if you make the curve smoothen, you will return many things, right, which will improve the recall. What is recall? Out of all the correct answers, how many have been returned, right? So if you return many things, because this is getting uniform, you are not able to distinguish between tokens. You distinguish between classes or whatever output. You return many things that will improve the recall. That's it, right? So now this is the KD paradigm in general. This is still a very active research area, and the good part about this area is that there are not many people working in this area. Although it's a very interesting, important area, because whenever, as I mentioned, whenever this kind of big models come, it always comes with a distilled version. Okay, so we stop here, and next day we move to the next chapter. Thank you.